that mean? If I yield a material, what does that mean?
It can no longer be hardened.
Means it's getting weaker from that point on.
Or any more deformation, it will break.
You're close. We were talking about plasticity and elasticity, right? What is elasticity?
It's point of no return.
This, the yield strength is point of return, right? So what is elasticity, guys?
The ability of something to not break.
Yeah. So if I take
Deform without factory.
here, I'll show you this paper clip right here. I take this paper clip. It's a perfect paper clip, and I pull this out. I pull one of these arms out a little bit, and I let go. Right? It goes right back to where it was. No change. What if I take this arm like that? What did I just do to it? I just yielded the material, right? So if I take, right now it's at this angle, and I pull it a little bit, it goes right back, right? I go a lot, I yielded it. It's not going back, right? So that means I've taken it into the plastic region, right? So all this through here, that'd be the elastic region. If I pull this all the way to here, say I pull it to there, I've got this much stress, I've got this much strain, and I let go of it, it'll go right back to there, right? It's going to go right back to 2 inches. So say it was 2 inches and 5 thousandths, I let go, it's going to go right back to 2 inches. But after I get past this point, I take my paper clip, I bend it past that point, it's not going back, is it? So I yielded it. So that means I've gotten into the plastic region. So anything past this point, it's never going to go back. It's irreparable damage. Right?
You can always keep yielding it.
Yeah, you can.
Anywhere in between there is where it can be yielded, but once you hit that X, it's broken.
No, you only yield it once you hit there. You don't ever want to yield a material, usually. I mean, you don't design things like, oh, if this tank drives across this bridge, it's going to yield the bridge, right? No, probably not a good idea. You probably want to stay in this elastic region. So, you don't really want to ever yield a material on purpose. It's usually not a good thing. Once you're at the top of the curve, up there, look, this should give you a hint here. It's the most stress it can withstand, right? Before it breaks or anything, right? The most stress ever it can withstand. So that's what we call the ultimate strength, or the tensile strength. Either one. You'll see it both ways, tensile strength or ultimate strength. That's what they mean here. Right? That's what that is. After this section here, you have this whole area, and then you have breakage right here. This whole thing is called catastrophic runaway. Because once you reach this point, you're getting a huge amount of strain. I mean, look at this. You're moving this much into strain, and you're only reducing stress. So that's the point where it's just pull and break it. There's really no stopping it. Once you go like 1 pound after this, so say I've got, I don't know, 4 tons pulling on this piece or whatever. And then at 4 tons and 5 pounds, I've reached all through strength. 4 tons and 6 pounds, it's going to just break. It's going to catastrophically run away and it'll break. Right? So that's where it fails. So this stuff coming back, you guys remembering it? Alright. So it's important stuff when you're thinking about what you're selecting, when you're selecting materials, how you're designing stuff, right? It's also important when you're manufacturing because you got to think about this stuff. Depending on the types of tools you're using, what materials you're cutting, how rigid the machine is, this all deals with this, right? So that's why we're talking about it. Any questions on any of this stuff? Do we need to do any problems or anything?
Did you give us like a sheet or something with all the terms on it? Or something?
There's a packet.
Some of them are in that. Some of the terms are in there. I don't think all of them are. The other ones are on the PowerPoint that should be in Blackboard.
Ouch. Yeah.
So sigma stress and that's strain. Force.
This is straight.
What about double shear?
Sigma and then the S stands
It's
for
straight.
strain. So sigma and strain, not stress and strain.
Yeah, it's not. No, this is stress. Sigma
Stress and strain.
Stress and strain.
double shear, like horizontal shear?
No, double shear is just when you have shear in two different spots, and that's all
Yeah,
it is.
alright.
It's the same thing.
God.
So here's what we're talking here. The elastic region, right? The plastic region. We have the tensile strength or the ultimate strength. Your rupture strength. All this is catastrophic runaway, right? That's probably a stress strain curve for a very hard steel. Very hard. They talk about the modulus of elasticity, which is basically the slope of this. You don't have to really worry about that. Here's a more typical stress strain curve. If we were to actually do a test, that's probably what you would see. Is this little wavy stuff here. That's usually how it actually looks when you're actually pulling something. So, yeah, most of the stuff's in here. Talking about stress risers at the end. So, all right, so let's start talking about some speeds and feeds. So, somebody have their book?
Nope.
Anybody have their book? Can borrow that? So one of the reasons we're talking about this is because when you're cutting something with a tool, what's happening right here? It's a type of stress. It says it right there.
Plane of shear?
Yeah, it's shearing, right? I got the lattice here and I got the lattice here, and it's shearing along a pretty clean line. And this line is continually moving with the tool, right? Ahead of the tool. So if you think about it, the tool is actually not shearing the material itself is shearing it. The tool is just kind of pushing it along. So that's why it's kind of important to know how the shear works and everything.
So, is there a specific angle for that?
With the angle.
Of that shear plane?
The shear plane depends on the rake angle. So that's what these are showing you here.
But the shear plane's never smooth?
Huh?
The shear plane's never smooth because does it depend on the lattice?
What do you mean smooth? What do you mean by smooth?
Because you know how you said the lattice is straight, right? And it will break along that, kind of like the grain.
Yeah.
So you said the rake has the ability to change the angle of the shear plane?
Yeah, this will move up and down depending on what this is. So like that. And it also depends on the material itself. So like if you're cutting some sort of hexagonal structure rather than a cubic structure, it's going to shear a little differently. Because hexagonal shear usually happens along the base. So you got these, pentagon thing. You got these like things that look like that, and they're bound. There's a bunch of them bound together. They usually shear right along that base because they don't have much. There's not much holding them together there compared to the long sides. It actually talks about that talks about graphite or something in the very first part of this. But stuff like titanium's hexagonal. Magnesium's a hexagonal structure, so it depends. Well, what you definitely need to know is that this shear plane is here, and that shear plane is created by the tool. All right, and you can see this in the chip. Actually, if you look at the chip, the back side and the front side, you'll actually see those grains like elongated. They actually get kind of distorted after that. So the chips are very hard because of that. They're gonna be a lot harder than material because they've been cold worked. They've been, the lattice structure's been deformed like that. So, Here's a pretty good photograph of what's happening here. You can see it kind of right there. And you can see how the grains, this is a real photograph, it's not a stupid cartoon, but you can these are the grain boundaries, right? That's a grain boundary. This is probably steel, there's probably some perlite in there and stuff. Pushing right along here, and the chips kind of forming like that. Push along this is a very small rig angle here, pretty much. It's not, like in the videos we were watching, it's like 30 degrees, right? Which you wouldn't ever use out in the, like this picture right here, that you probably wouldn't ever use that. That's not too bad, but the one in that video, you'll really be able to see it in this video now that you're looking for it. What is going on with this projector? Alright. So you can see right there. And you can also see the grains are really elongating right there. So what's happening right here? What's going on? Well, these things breaking off of the burrs, right?
That's a chip right there.
But what you actually have right here is a built-up edge. So the tool is actually not doing the cutting. You're just pushing material. You're shoving that material into there. So it's making the tool a lot harder to work. But you can see that thing's really, that looks like butter or something. But still, you can see that plane of shears right there. Almost at a 90-degree angle to that rig. So you guys can watch this in the dark.
Yeah, we watched it.
Light some candles. So like that was a positive rake. You can also cut with a negative rake. You don't really use it that much. It just protects the cutter, and it's not very common. This is usually what you want. Positive rake.
Seems like the negative rake could be harder to work.
It takes more horsepower. It takes a lot more power to cut, and it's harder on the. You got to have a really rigid machine to do it. So it's pretty cool how chips are formed. It's not like wood or anything. A lot of people think for some reason that it's a lot like wood and it just splits along something, but no, it's actually just shoving it and it's causing that shear plane and then the chip forms. So, all right, let's talk about some speeds and feeds here.
Please.
Now that you know how chips are made, right?
I just feel so dumb after today.
Are you gonna push that? Or did you? What the hell?
Don't they have remote controls for those things to adjust them?
No, I don't think so. You gotta listen to bolts. Screws in here.
You want to stand
Get some
on the
duct
chair?
tape. That's what I do with my projector.
Let's get screwdriver.
On wheels?
What if you were doing
I'm a skateboarder.
Oh, God.
Yeah, they're pretty bright.
There's 3 screws.
Well, it looks like the middle one's only pivoting.
You want me to do it? I weigh like 100 pounds.
Praise God.
Looks fun.
There we go.
Can you hold that position?
That looks good. How's that look, guys?
There we go.
Now it's shaking. Now it's seizure out there. Alright.
Just won't stop.
Why are those strings there anyway if they made that thing rigid?
The strings are there because this thing would like wobble super hard when the fans are on. So
And those strings are supposed to keep it stable?
I guess so. I don't know. I didn't put them on.
I mean, if it was a wired cable,
That could work, but
but it's like what? Cotton string, nylon string?
yeah.
It probably stretched quite a bit. I don't think you're doing anything now. A little tight. But anyway, so what we're talking about is speeds and feeds. So chip load. What is chip load, guys? Don't read the definition. I mean, what is it?
It's
When you did this your homework, what did you had to find the chip load, right?
Ah.
The feed rate, correct? So what is the chip load usually? Oh man, you guys are slacking.
Yeah. Well, we had a week off, man. It's like,
That's all right. That's why we're reviewing. That's why we're reviewing. So chip load is how big of a bite each tooth takes, right? So if I got this cutter and it's got chip load of 1,000, that means each tooth is going to take off 1,000th of the material, right? So if I turn this, it's got 4 teeth. If I turn it one time, it's going to take off 4,000th total, right? Because it's based on the tooth. So basically, it tells you how hard the tool is working. So obviously, if I'm taking a 10,000th chip load with the same tool, it's going to be working a lot harder.